Hello students. So today we are going to talk further in the chapter guys simple harmonic motion. So today I am going to talk about the tool which is known as phasor diagram. Okay, phasor diagram. So this is guys, this is a one of the tool which is very handy if you know how to use it. Okay, if you know how to use it, the method of like doing the algebraic calculation and getting the answer in the simple harmonic motion, in the lot of cases you can avoid and you can solve the problem with this phasor diagram method. Okay, so it's a very good technique, okay, to solve the problems. So we will try to understand in depth this concept, and then we will see some examples to understand this idea. So basically guys, this method you can understand in a much better way when we will take a lot of problems. Okay, so what I feel, with the problems, this method can be uh, grasped by the students in a much more easier way. But first we have to understand the concepts also. Okay, so let's see guys, without any further ado, I'll start the discussing the concepts. So guys, if you see, suppose if there is a particle. Okay, there is a particle, there is a particle guys. Okay, just for the showing the presentation, I am using guys a spring block system, but it can be replicated, or you can use the same idea for the other cases also guys. So this is a spring block system, this is a block uh, here guys. Okay, and this is your spring, and right now let's say the spring is in what, in its natural length. Now guys, it might have its amplitude. Okay, amplitude in this range. Okay, let's say this is the range in which it is going to oscillate. So it is the, you can say, the negative extreme, and this is the positive extreme. If I take this as a what, origin. Okay, if I take this as a origin, so this will be guys what, the, if you see, this will be the positive extreme and this will be the negative extreme if I take this as a what guys, origin. Okay, so this is your origin. Now guys, what I'm going to do, I am going to make a circle of this radius. Okay, with this radius guys, this radius I'm going to make a circle. Okay, this radius I'm going to make a circle. So let me make a circle guys here. Okay, yes, so guys, we have made a circle here. Now guys, what I'm going to do, I am going to assume a imaginary particle, okay, which is going to do a circular motion on this circular path. So guys, I'm assuming a imaginary particle here, which is right now guys at this position. When this, our real particle, when the our real particle is at this position guys, our imaginary particle is right now guys at here. Okay, now suppose guys this amplitude is a, suppose guys this amplitude is what, a. So the radius of the circle on which guys this imaginary particle is going to move is also going to be what guys, a only. Now suppose guys your particle, the actual particle, spring block system, it is going to move on this horizontal table with the amplitude a guys and the angular frequency omega. Okay, let's say guys the angular frequency with whom it is going to do the SHM is what guys, is omega. And now my assumption is guys, what my assumption is, my assumption is that this particle, this imaginary particle is going to rotate on this circle. Okay, it is going to revolve on this circle with the magnitude of angular velocity, whose magnitude will be what guys, omega. Okay, means this particle is going to move on this circle guys with the angular velocity omega, and where omega is what, this angular frequency only. Okay, this angular frequency only. Then what is my claim, what is my claim, my claim is that the shadow of this particle, the shadow of this particle on this x-axis. Okay, if I call this guys x-axis or the horizontal table, what my claim is that this shadow is going to the shadow of this particle, guys, the shadow of this particle is going to show the position of this particle, the actual particle. Okay, it is going to you can say uh, show, or you can say replicate, or it is going to tell you the location of this real particle at every moment. So the shadow of this imaginary particle on the x-axis is going to tell us where the real particle is going to be, so guys, if you see this, I am going to prove it to you. So if you see, guys, suppose if I take the suppose guys, this particle, our particle, is moving in the positive axis, and this is also, guys, what, moving in the clockwise direction that we are assuming. And right now, guys, we have assumed that it is what, at this position. Okay, this is the mean position of the particle, and this is what, guys, the starting position of our imaginary particle. So guys, in the, if I want to write down the SHM equation for this particle, we know that is going to be how much, guys? That is going to be x is equal to a sine omega t plus 0, because it is at a mean position and it is going in the what, positive direction. So guys, x is going to be what, x is going to be a sine omega t. So at any time t, guys, it should be equal to what, a sine omega t. So guys, if I show you, okay, if I show you that in the t time, let's say that the particle has gone to this new position. Let's say, guys, the particle has gone to this new position here in the t time. Okay, so this will be how much, guys? This will be a sine omega t. Now guys, if you see, in the t time only, our particle has go to what, guys, this much, and the angle that it will cover, guys, is how much, omega into t. So what I am claiming is, guys, if you see, the shadow will be what, shadow will be just above, sorry, at the same position where our particle would be, because guys, if you see how much horizontal displacement has happened of this particle, if you see, guys, that is nothing but what, that is a sine omega t only. It is, guys, what, nothing but what, a sine omega t only. So it means the shadow of this, guys, if we are dropping the light from this side, guys, okay, if we are dropping the light from this side, the shadow of this is going to fall at the what, at the same very place where the particle would be. Okay, so guys, if you see now, as this particle, if you see, guys, as this particle is going to get here, the my particle would be here, guys, and this will be here, it will come here only. And guys, when it goes to going back, okay, suppose if it is going back, guys, it is here. So particle would be have, guys, if you see, I'll try to show you, 1 minute. Guys, just a minute. Okay, if we take, guys, like this, suppose when the particle is reached here, guys, okay, our particle have gone, is if 1 minute, is as the particle reach here, our particle also moved here, and guys, giving the shadow here. Okay, as the particle reach here, our particle will be here and giving the shadow here. Okay, as your particle will reach here, this particle will reach here, guys, okay, and giving the shadow. So I hope you are getting the idea, guys, that what would be happening actually. So this particle moving, and guys, its shadow at every moment is giving you what, the location or the position of what, this particle, that where it would be. Okay, where it would be. I hope this idea would be settled for you. So now, guys, because you have understood and a bit visualize that what is happening in this, what I'm going to do, I'm going to take some examples and I'm going to show you that how the things would be happening. Okay, how the things would be happening. So let's take a example, a very simple example, guys, I'm taking, and I'm going to solve this problem with the help of what, Phasor, and then we will build up a good number of illustrations and with a very good quality of problems to crystallize this concept to you. Okay, so guys, let me take one problem for you. Okay, so guys, problem number one. So guys, it is saying like this, that a particle is doing an SHM having mean position at origin and amplitude of amplitude of amplitude of 5 centimeter, and its time period time period is time period is 2 seconds. Find how much time the particle will take. Guys, here I am just putting minimum time. How much minimum time the particle will take to go from 4 centimeter to minus 3 centimeter. Okay, to go from, guys, what, 4 centimeter to minus 3 centimeter. So guys, this problem can be solved with the what, with the regular our algebra method also. Okay, but I am not like going to do with this. Okay, if you want, you can solve with the algebra also. I'm going to show you that how we can do this problem with the help of what, our phasor diagram. Okay, so guys, let's see the solution of this. Okay, so guys, if I write down the solution, so guys, if you see what is given, I'll go on the next page only. So guys, if you see, suppose this is the phasor that we want to draw. Guys, this is your origin. Okay, this is your origin, and guys, this will be how much? This will be 5 comma 0, and this will be what, guys, minus 5 comma 0. Okay, because the amplitude is what, guys, 5. Okay, and the particle is, guys, right now when we are starting the study, is at plus 4. Okay, is at what, guys, plus 4 centimeter, and it has to go at what, guys, it has to go at minus 3 comma 0. Okay, so it is, guys, at 4 comma 0, and it has to go what, minus 3 comma 0. So guys, now there are two possibilities that might happen. So because they had asked for the minimum time, we have to think about that also, guys. So first I'll show you what are the two possibilities. Guys, suppose if the particle was going like this and then going like this, guys, so means the possibility is that it might go like this. That is one possibility, in which this time will be what, an extra time, guys. Okay, this time will be what, guys, an extra time. That is one possibility. And guys, second thing is what, maybe he is just returning towards this only directly. Okay, means it has gone to here and here, and then after here it is going like this. So this would be the possible minimum time, guys, that you can have. Okay, I hope this idea is very much clear to you. So if you have understood this idea, guys, now I can solve this problem for you. So guys, if you see, it means that our particle, okay, our imaginary particle, which would have started from here, right now would be what, guys, right now would be at this position, because then only the shadow would be what, getting formed here. Okay, is this or not? So guys, now my particle is moving like this, and your particle will be, guys, what, going like this. Okay, and it is gone here to here, and then, guys, what, the shadow will get formed here. Okay, so if you see, you have moved my particle from this to this position, guys. So this much angle has been covered. Okay, this much angle has been covered. So let's find out this angle, guys. So if you see, this is 4, this is 5, so guys, we can say this angle will be what, simply 37 degree. Is this or not? And guys, if this is 3 and this is 5, this will be what, guys, 53 degree. I hope this is you're getting. So theta would be easily, guys, we can say it is nothing but what, 90 degree. Can you see or not? Okay, so theta will be what, guys, 90 degree. So because to cover to cover 360 degree, it takes 2 seconds. 2 seconds. So to cover 90 degree, it takes 0.5 seconds. Isn't obvious, guys? Okay, so it means we can say that the minimum time required, so that, guys, we can say the minimum time required to do so is 0.5 seconds. Is this or not, guys? Okay, so it's a simple problem, and you see a very elegant solution to solve this simple problem, guys. Okay, so maybe you can feel that, sir, even we can do with the algebra. Why do we do all these things? Okay, so, guys, see, this is just for your what you can say, the introduction, that how do we approach this problem in another way. But the the power of this method you can see in the upcoming examples. Okay, so I'm going to take few more examples, guys, okay, to show you that what is the problem, what is the power this method is having. Okay, it is possessing. Okay, so, guys, problem 2 problem 2 for you. Okay, problem 2 for you, guys. So now, guys, let me read this question. Okay, so this question says like this, guys, that two particles, okay, now two particles are there, guys. Okay, so two particles executing SHM executing SHM SHM about origin along x-axis along x-axis, that their coordinates along x-axis and their coordinates are are given by x1 is equal to a1, sorry, a only, guys, a cos omega t, and x2 is equal to a cos omega t plus phi. So this is given to you, guys. They are asking, first problem, find the maximum separation find the maximum separation possible between the particles and second is, guys, what, find the time at which there find the time at which for the first time their separation would be maximum. So, guys, now if you see this problem looks what, a bit like tricky. Okay, guys, so if you want to solve this problem with the algebra, of course you can solve this problem with the algebra also, guys. How? Separation is what, guys? Separation is nothing but what, x1 minus x2, that is the position difference. Okay, so that will be what, guys, a cos omega t minus a cos omega t plus phi. So a you will take common, so cos omega t minus cos omega t plus phi. So, guys, now you can apply the formula cos c minus cos d, and then you can simplify that function, and you will get some function of delta x in the form of what, t. So guys, that delta x you have to maximize, is you have to differentiate that function, and then you will get some t at which it is going to happen. That then you put that t into what, that delta x function, and then you will get the delta x, which is what, going to be maximum. Okay, so this is the proper way doing this question with the algebra, guys. But of course you can see that it is going to be a lengthier approach. But guys, if we use this phasor diagram method, guys, we can pull this off with a much ease. Okay, we can pull this off with a much ease. So I'm going to take this method and I'm going to show you guys how to approach this problem. If you want, you can pause the video, you can try by yourself also. Okay, so guys, let's see this. So solution. So guys, what I'm going to do here, if you see, I take a circle here and we are having two particles. So I'm going to show them with the two different colors, and then we'll see that how do we solve this problem, guys. So one is, guys, what, one is given, if you see, guys, one is given x1 is equal to what, a cos omega t. Means, guys, if you put t equal to 0, x1 is going to come plus a. It means right now it is at what, positive a, guys. Okay, it means right now your particle and my imaginary particle both are, guys, at this place only. Okay, both are at what, this place only. And guys, the second one, the x2, okay, if you talk about, that is what, a cos omega t plus phi. It means it is 5 phase ahead of what, the x1, guys. Okay, it means what, my second particle would be what, guys, at this position. Okay, this position, and this will be what, guys, your particle. Okay, so my imaginary particle is right now here, guys, and its original particle, guys, it will be here actually. Okay, I'll show with some way if I can. Yeah, I think that would be way, guys. Okay, so these are our two particles, guys. Okay, so if you see, this is the position of these two particles right now, guys. Okay, so if I want the separation between them, okay, if I want the separation between them, that what would be the separation and how it could be maximum, I'm going to show you something, guys. Okay, so if you see, suppose, guys, at some moment, let's say at some time t, guys, this is your guys, the particle 1. This is your particle 1. Okay, this is for x1. Okay, and let's say right now it is here, guys. So in the this blue one, it will be a little ahead. Okay, it will be a little ahead. So I'm going to show this one, guys, with the some other color, just to show you. I'm going to make it with the blue only. Okay, so guys, I hope you understood what I'm doing here. So guys, this is here, and of course this angle will be what, phi, as it will be what, phi, guys. Just they have moved a little bit further, guys, and this will be what, my this particle, guys. I hope you're getting my point. So guys, this would be what, your separation. This would be what, your separation, delta x, guys. If you see, this delta x is nothing but what, it is nothing but what, guys, it is the shadow of what, if you see, guys, just a minute, guys, if I make this line, if you see, guys, the shadow of this rod, okay, is the separation. Okay, the shadow of this rod is only the what, guys, the length of the separation. Can you see? So if, guys, what we can do, if we can maximize this length of shadow, if we can maximize this length of shadow, then, guys, automatically that would be what, our maximum separation. That would be what, guys, our maximum separation. So now if I ask you, guys, when this can happen, when this can happen, so of course, guys, when this rod will become parallel to the x-axis, guys, then only you are going to have what, the maximum shadow length. Maximum shadow length is going to come, guys, when it is going to be what, parallel to what, parallel to the x-axis. Okay, so that we have to make it happen. So if we can make this thing, guys, we can solve the problem. Okay, so let's first find out, guys, what would be the maximum separation that is possible. So guys, if you see here, what I'm going to do, suppose, guys, either I should remove this. Okay, or I should make a different one. Okay, let me make a guys different one for you so that I can show you. Okay, so guys, let's see. If I make this here, okay, if I make this here for you, so this is guys our x-axis, this is our y-axis, and let's say guys this will be our what, the yellow one, okay, the first particle, and guys this is our what, the blue one, this is our second particle, and guys right now it would be somewhere here. My bad, I want guys this with a bit perfection. So guys if you see, it will be somewhere here right now, and guys this will be what, it will be somewhere here actually. Okay, and guys now if you see, this would be our what, this would be our guys this distance, and this will be our guys what, the maximum separation, delta x max. So guys if you see, this and this will be equal, and this is nothing but guys what, this is, we know that that is what, 5 only, so this will be what guys, 5 by 2, this will be also what, 5 by 2. So guys we know that this is a, this is also what, a. So guys delta x is nothing but what, if you see, this will be what, a sine 5 by 2, this will be also what guys, a sine 5 by 2. So delta x is simply guys, we can write delta x is, delta x max is nothing but guys what, 2a sine 5 by 2. Okay, and now the question that I had asked is what that how much the time it will take to happen this for the first time. So guys if you see, our particle, yellow particle was guys here at t equal to 0, and now guys it has just gone up to this to make it happen. So guys if you see, this angle, this angle, okay, this angle is nothing but what, 90 minus this angle. Okay, 90 minus this angle, which means guys this angle would be what, this will be simply pi by 2 minus what, 5 by 2. Okay, so we can say guys that the t, okay, to take this for the first time is what guys, pi by 2 minus 5 by 2 divided by what, omega. Okay, pi by 2 minus 5 by 2 divided by guys what, omega. And the same thing guys again will happen, it will happen guys again when they both will reach guys here, when they both will reach here, then here also guys it happens. So if you see, in a one time period it is going to happen guys twice. Okay, so we can say for the first time it happens here, and then plus t by 2 guys it is going to happen again, and then plus t by 2 again, it is going to happen, something like this we can do this problem. I hope you understood. Okay, so guys this is the question, and you can see the elegancy of this problem. Okay, you can see the elegancy of this problem, and of course the method, of course the method is so beautiful to solve this particular problem guys. Okay, so I hope you understood this problem. Now we can go for one more problem guys to show you how do we solve this. Okay, so I'll take one more problem, and then I'll discuss the guys position and velocity phasor, okay, in the next lecture. Okay, so I'll take one more problem to make this idea more concrete in your mind, and then we can see one more lecture guys on velocity and position phasor diagram. Okay, so that we will cover in the next video, but for right now guys I'm covering I'm taking one more problem for you. Okay, so guys if you see, problem number 3, problem number 3. Okay, problem number 3 guys. So if you see guys, this problem is saying like this, that two particles, again guys, okay, two particles, p1 and p2, it is most of like, it is more like guys inspired from the previous question only, and it is a bit easier because now you have known the idea that how do we approach these kind of a problem. So you can see this problem by yourself also if you want. So two particles p1 and p2 are forming performing SHM along the same line, along the same line same line about the same mean position, about the same mean position, about the same mean position. Initially they are at the they are at the at the positive extreme positions, positive extreme positions, positive extreme positions, if time period of each particle, if time period of each particle is 12 second, is 12 second, and difference of their amplitude is, and difference of their amplitude is, amplitude is 12 centimeter, is 12 centimeter. Find minimum time, find minimum time after which their separation between the particles, after which the separation, after which the separation between the particle becomes 6 centimeter, becomes 6 centimeter, becomes 6 centimeter. So guys, if you want, you can try, okay, you can try this problem by yourself. You can pause the video here. Otherwise you can look up to my solution that I'm going to do, guys. Okay, so if you see guys, here solution. Okay, so guys, here if you see, there are two different amplitudes are there. Okay, but the mean position is same, guys. Okay, the mean position is same. So what I have to do, I have to make two different size circles, guys. Okay, so what they have said, two particles P1 and P2 are performing SHM along the same line about the same mean position. Initially they are at the positive extreme positions. If the time period of each particle is 12 seconds and difference of their amplitude is what, 12 centimeter, find the minimum time after which their separation between the particles becomes what, is 6 centimeter. So if I draw, guys, I'll draw like this way. Let's say this is the, there is one which is at its positive extreme, so it should be here only. This is A1, let's say, and then of course there would be another, I think I should change the color, that would might look better. Okay, okay, I'll have to just relocate this bit. Yeah, I think it looks good. So there is what I'll do, guys, the other one is also here, guys, at its positive extreme, and this is what, this is A2, this is what, A2, guys. And what has been said, guys, that they are having same time period, guys. If the time period of each particle is what, 12 seconds, guys, it means that their angular velocity is what, same, because if time period is same, guys, angular velocity is also going to be what, same. So what they are asking, find the minimum time after which the separation between the particles become what, is 6 centimeter. So guys, let's say if this moves in t time, guys, somewhere here, so the original particle will be, guys, what, somewhere here, and at the same very moment, guys, this would also reach here, and guys, this will be what, here, this will be what, guys, here. This is your mean position. So guys, this is what, this is your separation, this is your separation, and you want that this should be what, 6 centimeter. Okay, So we can say guys this will be also what, 6 centimeter. Okay, and guys if you see uh, this is the difference between a1 and a2 guys, that has been given to you. So guys that is how much, that is 12 centimeter I guess, na? Yes, the amplitude difference is what guys, 12 centimeter. So guys this distance if you see, this distance is nothing but guys what, a2 minus a1, a2 minus a1, and that is what guys, 12 centimeter. So guys if this is 12 centimeter, we can find this angle, that how much angle it has covered. So guys if you see, what we can say, cos theta is equal to 6 centimeter divided by 12 centimeter. So theta is equal to what guys, theta is equal to 1 by 2 it is coming guys, so pi by 3. Okay, so theta is what guys, pi by 3. Theta is what guys, pi by 3. It means what it is has asked guys, that find the minimum time after which the separation between the particles becomes 6 centimeter guys. So we got the answer. So guys how much angle you have to cover, 60 degree. So guys if you see, time period is given what, 12 seconds. So guys in 12 seconds you cover how much, 360 degree. Okay, so guys in how many seconds you will cover what guys, 360 degree, sorry 60 degree guys. So if you see 60 degree guys, okay, so 360, sorry is 12 second per 360 degree into what, 60 degree guys. So this will be what, 6, this will be what guys, 2 seconds. Okay, so guys the answer would be what, 2 seconds in which it is going to happen. So if you see guys, this problem is also very elegantly guys can be solved with the using what, phasor diagram. Okay, so I hope you understood guys this method. Now then in the next lecture guys, we are going to discuss the phasor diagram phasor diagram of position versus velocity, and we will see that how this diagram method is what is a bit unique, and we will see some problems to understand, to solve the problems with this technique guys. Okay, so that's it guys for today. I'll see you in the next lecture. Thank you.